All right, chapter 22. Chapter 22 covers alpha substitution of carbonyls compounds. So a whole variety of carbonyls, aldehydes, ketones, esters, amides, and so forth. We'll see these patterns in today. All right, so the key observation here is to recognize that in the keto form, when there is an alpha hydrogen, it's in equilibrium with the enol form. This is the tautomer of the keto form. So this is keto, not the diet, but short for ketone. This with an alkene and an alcohol is the enol form. Okay, and the tautomer is just a special kind of isomer. Okay, so we've moved a hydrogen to oxygen and put in the double bond. What we will also learn that's especially important in this chapter is that we can deprotonate with a base. And we form the enol 8. Like if we had methyl oxide or something, it's the equivalent, or deprotonated the enol. This is the enolate form. Both of these react with electrophiles Now I'm going to push a little bit of arrows here just to make it easy and obvious for us. There's a lot of electron density at oxygen, and in fact, like we saw for conjugate addition, we had a bidentate electrophile. We have a bidentate nucleophile. It is nucleophilic at the oxygen, of course, but there's a resonance form of this. And from this resonance form, you can see that it is nucleophilic at the carbon also. So it's nucleophilic at either end. For most of the things we're going to deal with, we will see reactivity at the carbon end. So the lone pair of oxygen comes down to reform the double bond. We swing out the pi bond and attach the electrophile at the alpha carbon. So these carbons, here's the carbonyl carbon, and this is the alpha carbon, and we count the atoms as we move away, as we've already seen with conjugate addition, alpha, beta, gamma, delta, epsilon, and so forth. So these both react with electrophiles to make a new bond at the carbonyl alpha carbon. So this is the alpha carbon. It is both acidic, and in the enolate and in the enol form, it is nucleophilic. All right, so that's the fundamentals of tautomerism and an overview of what we're going to learn about in this chapter. Now let's look a little bit more in depth here at tautomerism. So if we look at some simple compounds, cyclohexanone is in equilibrium with its enol form, but there's not a lot of it, right? It's 99.9999% keto and 0.0001% enol. Now, why do I mention something that's such a small number? It's because even though it's only 1% or 0.0001%, it's still highly reactive. And so, again, by Le Chatelier's principle, if we react via the enol, we'll shift this equilibrium. And so we can see chemistry that funnels through this. Do you remember the potassium permanganate oxidation that I talked about a couple chapters back? It was on exam 2, where we saw the potassium permanganate breaking that alkene bond. Another example for you here is acetone that's in equilibrium, again, highly favoring the keto form, in this case 99.9999999% keto, so that's 0.0000001% enol. But again, we can funnel through that if the chemistry is fast and efficient. Now, not everything obviously is this way, and of course we're going to learn how, with the proper base here, to convert those to enolates quantitatively. So let's take a look at one other substrate or ketone here. This is 2,4-pentane dione if we consider its equilibrium. And I'm going to put in some added features here with this enol. There's actually an intramolecular hydrogen bond here. These protons are alpha to 2 different carbonyls, and we're going to learn that makes them much, much more acidic. And notice that this enol is conjugated. The alkene is conjugated with the double bond. So in fact, this compound is 24% in the keto and 76% in the enol form. So depending on the details of the structure, it can be majorly enol. But of course, we've already seen some enols. I alluded to this in a prior lecture. Phenol is 100% enol. Right? Remember, we have that 36.6 kilocalories per mole aromatic stabilization energy, so its corresponding keto form just doesn't exist. We can make this as an intermediate, but it will almost instantaneously convert to the enol form. Okay, and this would have been the keto form. All right, now how does this keto-enol tautomerization take place? Well, first, there's an acid catalyzed process. So if we have an alpha hydrogen, and I'm only going to show the one, the other two are there, but just to simplify drawing and following along. If we react this with acid, of course, the lone pairs are the highest occupied, are in the highest occupied molecular orbital and the most readily available. So we protonate the carbonyl. So we now have that position, CH2H. If we have now the conjugate base, I'll write it as Cb of our acid, whatever it was there that was negatively charged, or a solvent molecule, what you see is that we have a protonated carbonyl. And of course, in this instance, it makes this position much, much more acidic, just like it made the carbonyl more electrophilic in acid catalyzed processes that we've already seen. So if we deprotonate, the CH bond swings down, the double bond swings up, now we have formed the enol. Okay, so that's the acid catalyzed process. Then we have the base catalyzed process. So if we add, let's just use hydroxide, here. It looks like one lone pair, should be two. So then we can do a direct base catalyzed elimination of that proton, essentially. There's the enolate. But of course, if you consider the basicity of water versus these alcoholates, there's a considerable equilibrium to protonate that and produce the enol. Now, I want to look for just a moment at how this reaction occurs, because you see, not every proton alpha to the carbonyl is the same. Let's look at acetone here for a second, and I'm going to illustrate with three-dimensional drawing the hydrogens. So what's important to recognize here is that for a specific conformation, these hydrogens in that instantaneous conformation. Now we know, for instance, that there's free rotation about these bonds, so that CH3 group is rapidly sampling all of the different sites. We knew that from NMR, for instance, if you recall. But it turns out that the pKa's of these hydrogens are different. Remember the p orbitals here, and this is looking top down on a p orbital. P orbitals in that pi bond would look something like this if we were looking down on them from the top. And so you see this hydrogen overlaps with that one, whereas this hydrogen here would be in the nodal plane of the pi bond. So this hydrogen is not acidic, and it might be something like, a little less than methane, because you do have the electron withdrawing effect of the carbonyl, but this is my guesstimate to give you a pedagogical conceptual picture, probably around 40. I don't know that I've ever seen that actually calculated or measured. Whereas this proton is much, much more acidic. In acetone, the pKa is about 19.3. And it's because this sigma bond, if I can draw in that orbital, there's the hydrogen, carbon with the sp3 orbital making the bond to hydrogen. That one overlaps with the pi system, and so the pKa is about 19.3. Now that's considerably less than 40 to 50. Okay. So we can access this readily. Sodium hydroxide, for instance, will give us some significant deprotonation of this. The other thing I want to talk about, because we have the pentane dione up here in my introduction and inclusion of acidity, is when we have a hydrogen here that's adjacent to two carbonyls. As I've drawn it, it's two ketones, but it could be two esters, or a ketone and an ester, or an aldehyde and an ester, or an aldehyde and a ketone. Anytime there are two of these groups that can overlap, the protons here are much, much more acidic. So the pKa of this is approximately 9. Okay, so acetone, right, was 19.3. I replaced one of the protons of acetone with another carbonyl group, and the pKa goes down by 10 to the 10th, right? That's 10 to the 10th more acidic, because remember pKa is the log-based number minus log of the Ka to get pKa. So that's a massive change in acidity. But of course, not nearly as much as going from hydrogen to ketone, right? Methane is a pKa of about 50. We replace one of the hydrogens with a carbonyl and it goes to about 20. That's about 10 to the 30th versus methane, right? So let me put methane up here. There's methane. And so the pKa here is approximately 50. So we go from 50 to 20. That's 10 to the 30th more acidic. That's humongous. And we put another one on, and we have a 10 to the 10th change. So the pKa is around 9. These are important properties and concepts for us to keep in mind as we now explore chapter 22 and the alpha substitution of carbonyl compounds.